Thank you for invitation and this kind of opportunity. My name is Tetsuya, Ogata from Waseda University. And also I work at ICE, Japanese National Institute of Industrial Science and also Technology or something like that. And now I'm invited research at the AI Research Center. So, as already Andreas introduced me, so here is my CV. And so I originally graduated mechanical engineering with mainly design the robot from the hardware design. And also work as human-robot interactions using the neural networks or behavior-based robotics architectures. And after that, so here is some, in Japan, some robot boom. So humanoid robot boom, so Ashimo, something like this. So after watching that on advanced hardware, I decided to move to more intelligent parts and software parts. So I moved to the Brain Science Institute. So where usually is almost all researchers work on the more biological system using mouses or something. But there are also application names as creating brain. So very, very engineering field. So where I work on the robotics and neural networks. And here I work at Kyoto University almost 10 years. So I continue the almost same work. And I back to the Waseda 5 years ago. So the title of the department includes intermediate arts. So as a main professor, I work on computer graphics, virtual realities, or something like that. But I still continue to work on the robotics and neural networks. So after the graduation, graduate school, I continued on almost same work. So the completely different institute, but I fortunately continued to neural networks and robotics. And here's a slide and just short introduction of Waseda University. So we have almost 50 years history to continue developing humanoid robots. So the first bipedal walking robot is developed in 1967, before I was born, made in wood. And this is the first humanoid robot in the world, named Wabot, Waseda robot, which weighted over 2 meters and 200 kilograms. And it takes 45 seconds for one step. Oh, I watched the movie, but I skipped the watch. Anyway, that's very impressive. And this one was to train organ and piano. And so continue working on this type of robot systems. But almost professor interested in hardware. So, but now I think that so we need to think about more about the intelligent part, especially so embodied intelligence by using the robot systems. So I'd like to join and collaborate with such professors to continue on the neuro-robotics research. And here is another stream in Japan related to AI research. So here is 3 persons. They are minister of these Ministry of Economy and the Ministry of Education and Ministry of Communication. Actually, 2 guys are already changes. Now there's only 1 female remaining. But anyway, this is the first trial to make a joint of the project related to AI. And this ministry established and defines AI Research Center independently, but try to collaborate this field. So, completely by the influence of the deep learning or such kind of new technologies in the AI field. And now I worked at here as an invited researcher. Okay, so I said and I continued on neuro-robotics, neural networks and robots for over 20 years. And this is the work on my PhD thesis. So the target is human-robot interaction. So Aibo, the Sony petrol. Because I hear the Aibo robots, I developed this type of robots. So the monitor and the interaction with the human using the sensor and tactile sensing may be very similar to the concept of the pepper. But anyway, 20 years ago. So this robot shows his emotional condition. We call it emotional, but actually it comes from his hardware conditions. So battery voltage, temperatures, motor, or circuits, or brightness around. So for the survive, to avoid the hardware collapse, the robot changes its conditions. Sometimes move very rapidly and slowly. And if it's tired, and he'd sleep by killing the switch of every motor or every sensor. That's something. But from these days, I saw that it's a very problem. It has only very poor intelligence parts. So, how to scalarize adapt to large scale data set of sensory model? That is always a concern. That's a problem I always concern. So then, now deep learning. Actually, I continue neural networks. I work on neural networks for 20 years, but then I started to use deep learning in 6 years or something. So maybe, especially for Japanese people, this is very impressive. And Go is a very, very popular example. So, some Japanese researchers said that it takes at least 10 years for the AI to overcome human top players. But actually, last year, the AlphaGo developed by DeepMind beat the human top players. And it's used for, of course, as you know, image recognition, speech recognition, handling the natural language processing or something. And but it was so many studies, still so many studies in the robotics field. Here is one example done by also Google. They use 14 robotics for training, the picking the everyday object, many different types of objects here. And it takes about 2 months for training. So, but finally the robot was success to any kind of object with an 80 or 80% success rate. Okay, so from now I'd like to introduce my research related, first related mainly application of the deep learning. So deep learning is usually well known as a recognizer, just a classifier. And this is a very typical for the existing conventional recognizer. So if given to the data of the big image and speech, high dimensions, human prepared some design from some features, for or MSCC or something like this, and put to some conventional classifier, SVM, HMM, something like that. But as you know, deep learning skipped this kind of human design parts. So deep learning can accept such a large data with high dimensional data directly, and can output. So it's called end-to-end learning. And even this kind of violent methods, it sometimes shows a better performance in the existing method. Sometimes shows better than humans. This is very old, not old, but just 2 years ago, work by us, our groups, with target in the speech recognition by using both information of the sound and image. So we are not specialized on speech recognition. Rather now we are using neural networks. And easy to introduce the deep learning techniques. So we tried to do this. We collaborated with Honda Research Institute. So here is the deep learning, which is for denoising. So some signal with some noises, and with trained for to out of the clear sound. And here is a convolution neural network to handling the lip reading. So the input in image, the lips, and output for the Japanese recognition. There are 40 types of different types of phones. So Honda had, I knew that Honda had good data. So that's the reason why I collaborated with Honda. And they create the many data with based on the ATR on imbalance part, and it is collected from the 6 makers. And we tested the different types of the image, so different size of the resolution. And using only one image, no, we didn't use any information about the sequence of the images, but word recognition rate reached over 20. So this performance at that time, this time, almost same performance as the state-of-the-art works. But here, last year, December. So, DeepMind released a new architecture named DeepNet. So, idea is very similar to by using convolution networks and recurrent networks, but they showed performance over 60%. The reason why I showed this slide is that they refer to our works like this. But anyway, so I think that just handling the data in the cloud, Google is strongest. Image recognition, and speech recognition, something like that. So that kind of categorization, classification tasks is all just depend on the size of the training data and the computational cost. So in this field, I think we cannot compete. So, again, I back to the robot. So the robotics, it's not easy because our final goal is not just classification, but generate motion. So this is normal flow to the generate motion. So obtain the sensory information and feed some exciting feature. And feed to some model, 3D model or some physical models in the function in the robot. And robotics engineer prepared some simple motion patterns or control theory, and then generated motion. This is very common. So here is a robotics researcher just use a library, OpenShift or something. And here is a very specific part of for the robotics research engineers. Well, if we consider sensors, back to the sensor deep learning, this architecture could be applied. So if we input sensory information, vision, sound, also current motion conditions, then robot can generate the motion or predict the future sensory information. This is our past work. We applied the deep learning technique to the robot work. I published 3 years ago. And here we taught the robot to the handling different types of objects. So firstly, we use a direct teaching manner. We made the robot to generate this motion. But during this motion, robots learn not only trajectory of the joint, but also the image, also sometimes sound. And here is actually we prepare the 3 deep learning models, data layer networks. Here is for handling the sound, of which inputs almost 1,000 images. And here is a neural network for handling the image. And so combining all information to the one, also another deep learning models, which handling the sequence of the image and sound and motion. So by using this architecture, the robot can predict or generate the next step of the current condition of the image or motion. After training, by using only 3 deep learning models, the robot can handle the object corresponding to the even different types of object, different types of situation. And it's of course, it's done easily. Well, this is another example. Here, in this case, is we cue the input of the image, and human just move the robot's hand like this. So this is a generated predicted image by deep learning from the motion input. So completely covered eye, there's moving hand, and imagine the image. Right? This is a generated one. This is an original, so correct one. So you can see the robot can predict image. And this, by using the same architecture, the robot can predict the future image. Actually, the window size here is only 3 seconds, so at longest, the robot can predict in 1 second future, 2 second future. But anyway, robot, we can check the robot actually want the given task by checking this little image. So now, in an AI center, AI research center, which is the target in the industrial robots, so we try to apply the same architecture, more complex robots, this type of human robots, for handling the closed towers. So it's already published in autonomous robotics and automation data. And here you can see the human here, and now he becomes the robot by using head-mount display, and here is 3D mouses. So he controls this robot and collects in many different stations, different towers and different posture of the towers, like this. And we tested many different types and another type, unknown towers. So here's an input is an increase like this, almost 40,000. And also in average, if the human operated the robot, it takes almost 70 seconds because head-mount display and 3D mouse is very not easy to handle. But then after training, the robot could holding the tower in 10 seconds. Okay, here is an architecture of our system. This is a deep convolutional autoencoder with training to the inputs and here captured by the camera. And here is an output. So it's trained as the output the same as an input. But here is the middle layer, which size is quite small compared to this one, so 40,000 dimension. This is only 50 or something. And this information is so that means compressed data here. And by combining the information of the joint, that means motion, it inputs here and so recurrent neural network. We call the multi-time scale recurrent neural network, MTRNN. So this network is trained to reproduce the sequence of the image and the joint. So this is one of the results that we obtained. So here is the input. And here is predicted, the future predicted by the recurrent neural networks. And in this case, we put the tau in an unknown position for the robot system. So you can see the robots seems to be having a little bit difficulty to predict the position of the hand. But anyway, you can see the robot seems to be succeeded to predict the future. Yes, this is one of the performance. So usually, so the existing study, it required many long time to map the image and 3D models to the internal robot. But now, thanks to the deep learning, it works very fast. So usually all the work it takes 8 times maybe or 16 times maybe. But now you can see the 2D. And this one is completely unknown. So this tau doesn't include in the training data, but now robot can. And finally, we put here book. So of course, this robot only knows the towels. So he regarded it as a towel. But now there's no problem. Almost same way. So repeated in this part, in this piece. And here is a movie. We exhibited this robot in the exhibit held in Hanover in the March in this year. And at that time, so we were represented with an AI research center. And at that time, some higher person said, please increase the speed more and more. So we tried. And here, this is moving 4 times faster than this one. This is a captured image. This is the predicted image. Yes, by decreasing this, some process, we can succeed to increase the speed. And here is the writing condition is unstable, and but thanks to the deep learning, the robot can adapt to such a change of the situation conditions. So now we apply this robot to handling the real process. Actually, it works. But in next, I will show the component I will show you. And okay, so move to next topic. So I mentioned the recurrent work a little. Here I'd like to talk more about how to use the recurrent process. And maybe Tetsuya, my student, already told here that his work. But I'd like to explain a little about his work. So now recurrent neural network in the context of deep learning used for natural language processing, especially shows a good performance for the translation from the different language, English to Japanese or something like this. Yes, I now recommend students to use it. And this block means a recurrent neural network which has connections, not only has input, output, but some internal connection. So here is first step, the second step, third step. So some internal condition, internal active state is to the input to the next step, the networks. Right. So here is the first sentence like something like in English. And here is some signal for the end of sequence here to the input to the recurrent networks. Then it's trained to output the Japanese sentence corresponding to English. So the human designer just prepares many sets of the such corresponding sentences and trains the recurrent networks. So now the networks can translate the English to Japanese. And here is the example, the research done by the Google, and they apply the same architecture for the conversation. So they prepared many huge data sets of the conversation between two persons and trained the recurrent network with that data. So after training, human can talk with the recurrent network. For what is moral, what is humanity, what intellectual intelligence is. What is immoral? The fact that you have a child. What is morality? What is the altruism? What is the definition of altruism? So if you don't believe the God, then you don't know something. So here, interestingly, this example I like, and interestingly, human asked almost same question again. What's more? So I'm not a philosopher. You are Fortune or something. Finally, he get angry or something. So this shows the difference, this network between this network to some bot, existing bot. Because some existing bot, usually this kind of sentence, is prepared by human designer. And the machine replied based on the keyword include the input sentences. In these cases, so he's repeated moral. So usually, like Siri or such kind of bots, finally say the same sentence usually. But in this case, thanks to the characteristics of recurrent neural networks, so internal condition is always changes and never repeated same condition. So the machine generates a new sentence, always generates a new sentence corresponding to the talking context. This is a very good example shows some characteristics of the recurrent neural network. And I applied an almost same technique for the robot system. So transfer from the sentence to the behavior. In the previous cases, so Japanese to English, and so sequence. And same as we can avoid so sentence to behavior. So it might be a good example in a sense. So one of the issues for the robot conversation is that so ambiguity of the sentence, the meaning of the sentence. For example, this is a setup, experimental setup. So I asked the robot to hit level first. So even the same sentences, robot have to change corresponding condition. Which side red bell first? If the red bell, there are two red bells, robot should hit both or hit one or something. Or if there is no red bell, robot have to ignore these points. So even this kind of very simple settings, there are over 140 possible combinations. And even we apply the more complex task for this kind of conversation, it is almost impossible for the human designer to prepare the all required versions. So I use such a sequence learning more to generalize such a correspondence between the sentence and motion. So in this case, we use half case or the combination for the training data and test it at 72 sequences for checking the generalization ability. I think that we can decrease the size of the training data. But anyway, in this work, we checked all other untrained cases, and we confirmed the robot can react, correct to the given sentence, even an unknown, untrained stage. This shows an activity of the neuron with the recurrent neural networks. Here we use only one recurrent neural network. And one neural network has a neuron for encode these words or joint angle of the robot and visual images. So only one recurrent neural network handles natural language processing and motion control and vision processing. Each of them are quite simple and cheap cases, but only one recurrent neural network can integrate all different types of activity. Here is a demonstration. This is an activity of neurons, the recurrent neural networks. And by using principal component analysis, we can see the main activity here. So if we input the sentence, this move to the change to the conditions, and following the motion. So now here is a scenery of the demonstration at the NIPS last year, and here we show the case, and we include the word of the or. Please hit the red or green, or and please hit the red and or something. And also we can apply to not hits. Okay, here until here talking about application, and as I said, so now Google, Facebook, Microsoft, and many other ventures and shows and developed many applications in the recognition, classification of the image and speech and text. Usually texturized and uploaded in the cloud. And I thought, as I said, in this field, Google is strongest. But of course, we have to think about and apply these techniques to more realistic applications like robotics on an automatic car or something like this. So, and I believe that by thinking about application of this real world, we can reconsider about the definition of the intelligence. Okay, so, of course, there is very, very big problems to how to collect the training data, or maybe there are many problems in law or application in the real world. Okay, so such my rethinking the importance of the body. So again, I'd like to introduce some research on the cognitive developmental robotics, so working on embodied intelligence. In Japan, some projects found which leader is Yasuo Kunioshi, is a professor of the University of Tokyo. He was started this project named Developmental Science and constructive developmental science. That means so to research and developmental science using a robot system or simulation. And from that, I'd like to show you my work by him. Okay, well, some of the people here know well about this work. So, so cognitive functions include many of those functions like this. And I'm basically an engineer. So I would like to improve the performance of the robot system. But to do this, so I would like to know what's the intelligence, what's the human intelligence. So under this approach, so not just analyzing or observing the activity of the brain, but try to construct brain with the body, like robot system. to understand human cognitive functions. Okay, here is one topic. Recently we published the names and two body assimilation models. So the target is to handling. And here is some phenomena called two body assimilation. That means human recognize two as an extension of his own body. So this is proposed by the Iriki sensei at the beginning. So he had an experiment with some monkeys, and he observed the activity of the neurons, bimodal neurons, and in the monkey. So at first, when the monkey captures his foot and hand, so some neurons activated. And he trained the monkey to pick the same food by using this kind of tool. Then after the training, so the same neurons activated here. So at first it is activated for the hand, but after training, the same neurons is used for the touching the chicken too. So it can be explained in many different ways, but he thought this is a kind of evidence, so human brain to modulate his own body scheme to extend it to the two. So this is the framework of the existing robots, so convolution robot system. So yes, like this. So in these cases, usually the human designer have to prepare the robot model and tool model. And also they have make the model so by combining. So these blocks are designed independently. But by introducing a sense of such a tool body assimilation, we can transfer this concept to here. So here we prepared some body schema. It could be modulated by the parameter. And if we put on some one tool here, then the body is changed. And if another tool here, the body changes like this. So by using the neural models, we can model this kind of scheme. Okay, this is the architecture we made. So maybe someone noticed this is almost same architecture of this one. So the robot for the holding the towers. And the only difference is here is that we add just 5 neurons for modulated the recurrent neural network's activity. So the robots here is a camera image captured by the head, and by using the autoencoder we compress the size of the dimensions, and body and motion information, vision information is input to the MTRL. But here is only 5 neurons to the modulate the change the activity of this. So first, we train the robot without any tools. Just bare hand, the robot try to move the object, many objects in a different position. And after training, every weight here is fixed. And we add 5 neurons here. And then we make the robot hand a tool. So by the tools, the robot have to adapt such a change of the body schema. But now these are fixed. So by changing only the 5 neurons activity, the robot can encode such different types of body schema. Okay, this is an experimental setting. We use an Actroid developed by Hiroshi Ishiguro. But then I little bit dislike his skin. I have this. And this one is using these different types of tools. And yes, and capture the camera and input the different models. Okay, so this is the result after training. We obtain the representation is PV. So this one. We call this one PV nose. So the represent the parameter bias. And here the red means the hand, bare hand. And blue is a screw, right, and hammer. And we also prepare the L-shaped hook, but it does not use it's not used for the training. So if we focus on the center, so here is some distribution because there are many different types of motion. But if we focus on the centralize on this distribution, we can find a clear structure. So always the handle is placed very far from the other tools. And screwdriver and hammer is placed here, and L-shape is placed here. So even the unknown tools, the PV, the 5 neuron, represent such difference. This is the scenario of training. After the bare hand training, we made a robot to handle this kind of object like this. And so as the same as in the case of holding towers, ropes, so the robot can predict the future image. And this is an experiment we set the final goal as an image here. And here is the current condition start. And by using the technique of back propagation through time, we found a sequence to connect from here to here. Then the robot can generate this kind of motion. Yes, so I think there is almost a time. This is, I think it's almost time. So I have also one topic, but it takes a little long time. So I try to conclude. So today, I introduce my current research on the application and also some academic researches on the deep learning. And as I said, so deep learning now is used for mainly classification of such as data-ized data. But we can reconsider to apply the models of cognitive developmental robotics to enhance the application of the deep learning to more realistic application. So yes, I skipped this topic, sorry. But so we already, so cognitive developmental robotics has a very long history. There have many knowledge to reconsider what the deep learning is. So my future work would like to connect to these two fields. Okay, thank you.
Sorry.
You go first, and then you go.
If you go back to the earlier slides where you show the full system for perception to behavior.
You mean here?
Yes. On the left, I see a box where it says planning.
Yeah.
How do you do it on the right?
Actually, in cases, so I use a recurrent neural networks. So for example, the holding towels.
So
We taught the robots the whole motion. But after training, we can find the recurrent network segmented these functions, so reaching the position and grabbing and something, the holding and reaching. And this timing is often changes, depends on the size of the tower, of position towers. So recurrent network have to adapt to the how to combine, how to shift such phases. So here, so recurrent network shows an ability to handling the grammar. So different size of the different type of the languages. So maybe this kind of ability is a help to the robot system to make some planning to how to combine different frameworks.
So to go back to the video story, when the planning is approaching the hand to the right place in the image.
Yeah.
So you replace that. There's lots of examples of different images.
Yes. So here, in this case, we made this motion in many different type of cases. So robot have to segment such motion. So in the internal representation of the recurrent networks. So some phase in the quality, some phase in the classification. But of course, it's very simple planning here. How to which ways it should go, how to classify.
On that very example, the size of the training data set is only 35 sequences.
Yes. Here is only 35. So we just only handle these squares, towers. So we change the shape of the towers, but this sequence is enough flow in this case. Because for the training the image, here the sequence of image. So actually the number of the images is quite large. So that is a little bit different from the case of the recognition, image recognition. This is this network have to regenerate all sequences. I think it's 5 seconds. So the total image size is quite huge.
Well, my question is related to Guido's as well. It's actually how do you achieve dynamic adaptation of basically this simple repeated task now? How do you dealing with adapt to changes when you quite I think we can particular specific neural network you use to actually helping with the plan and organization.
Okay. So may I change the different slides? This is we haven't presented yet. Now if I put this same picture to the okay, here now, so in the case of the holding towers and reaching, and in this case we clearly represent different types of motions for the opening box, picking the object, and closing the object. And all these motions are embedded in only one recurrent neural networks. As the same as manner of sentence learning, recurrent networks have trained with different type of sequences. And in these cases, I think there are many different ways to embed these different actions. But in this case, the robot changes motion to the according to the change of visual information. So firstly, it for which direction? Blue one, and yellow one, and red. So
when you say PCA, what does it mean?
Principal component analysis.
How you apply?
How?
Why it's PCA?
It's just for analyzing activity.
Overheating, what are the recurrent?
Yes, because it was has an over 1,000 or many neurons. So to the analyze how it changes, you will use this to just compress two images. So by adapting it, so here now changes the position. So the recurrent networks can adapt to such a change. Or this is so interacting humans sometimes, but the robot can continue to work. So by training with the raw image and recurrent networks, the robot can continue to work. So yeah, this is one of the ideas on how to implement the priming mode. But maybe there might be another way.
Can I please ask a question? Very exciting topic. So, as I understand, you take some sequences of images as an input.
Yeah.
So, how many neurons are there in the recurrent neural network?
Actually, so image size is quite large, but by using the default encoder, here is over almost 40,000 pixels and RGB. But so all encoded is here, so we compressed these size to about 50 neurons. So it's now combined with information the joint about 20 joints. So then includes the recurrent neural networks. So there might be many ways to the compress the image size. Now we are using autoencoder to confirm that this feature that actually compressed this images. But now if we increase the size of the resolution, so robot cares about a very small change of the image. So for example, interesting in these cases, robot have to see that his one arm during the motion. If we just focus on the clothes, robot can. So maybe he in the recurrent networks always try to correspondence between the image and the joint angles. So we need to do that little bit larger, wide range of the image.
Okay. Final question.
The idea to use artificial neural networks to train a robot using, say, human movement is not new. There are many people who do it.
Yeah.
But what is your secret? Why you are better than others?
Okay, so yeah, in that sense, it's my interest in concept on this kind of techniques, so that how to modulate. So the once networks are obtained for the body, but it could be used in another robot, or it could be used in predict other person, or it could be acquired robot with different type of tools. This kind of the topics might be new ideas. Yeah, this topic.
So parameter modulation.
Yeah, right.
I like it.
Plus, Tetsuya is one of the first to have used neural network for robots.
Possible, but I know many examples.
Okay, I think we stop here. So let's thank the speaker. Don't go away because we have the delayed launch of the joint seminar. Richard, if you want